Thank you very much. Good afternoon, ladies and gentlemen, as we say normally, mesdames, messieurs. I start to thank all the space agencies that really offer us to live such amazing moments that we just lived and we are still living. The next acknowledgement would be really for the orbital PIs. I like really to say that nothing would have been possible without an important cooperation within the entire Rosetta teams. It's not only a Philae endeavor, it's really a Rosetta endeavor. And those who spent weeks, months, still since July to really realize what the comet looks like and to help all what happened afterwards are to be thanks here. And I think of Olga, Fabrizio, Sam, all the people who know that they have invested themselves so that we are where we are now. So, just to remind you, we really had a dream, and 3 months ago we didn't know whether we would achieve it. And we wanted to land on a comet. That's something that we proposed 25 years ago, actually, and it's no time to make history here, but some of the room were here also 25 years ago, including our colleagues from JPL were in that train at that thought, and stupidly they were left over afterwards. So it's really something we wanted to do. We wanted to land there because we had the idea that the comet have clues really to help us decipher the processes and also the ingredients that are responsible for the diversity we see in the solar system now, and possibly also for the emergence of life. So it's not a trivial stuff. We wanted to do so for very high-level questions. And what we finally built is represented here. It's typically a cubic meter, 100 kilograms of system and payload, and we have 25 kilograms of payload with 10 instruments. And we had to manage, develop, and operate the entire stuff as if it was a PI investigation, although it was a little more than that, of course. And we coordinated that, and really it's a brilliant success collectively, and again, it's a collective endeavor. So as Jens just told you, we decided to select that site, and again, you know the reason why. Of course, we had the best places on this body to be there, and when we make the descent, it was exactly as planned. All the instruments that we wanted to operate did operate, and some of the results have already been presented. Some will be presented in the late session. It was really a very, very good sort of science that we decided finally to incorporate during the descent itself. Then, as you saw, we know where we were, which is only 100 meters from where we wanted to, and from more than 500 million kilometers, it's not that bad. So we really were very happy to make that happen in that quest. But rapidly, it became obvious that after the touchdown, we have left the comet. And that went from instruments and systems that demonstrated that we were flying just after the touchdown. We knew we had left. We didn't know at which velocity. The incoming velocity was higher than the escape velocity. So the question is, okay, during the rebounds, what part of the energy was dumped and what was the remaining we had? And we hoped, of course, that it would be lower than the escape velocity. We had also the CIVA panorama was supposed to make the first panorama after we landed. It's operated partially only, but I've never shown this image, so I will show that here now. CIVA is a set of instruments. It's not only the panorama, but it's a set of 7 cameras, very efficient actually, put all around the system. It's very small cameras, 50 grams cameras, all around just for redundancy, and that's why it's named CIVA, because we have 7 arms and 1 brain. And that's the reason why we call that CIVA. And actually the same camera is also in many other places, including the COMSISCOP that Yves just delivered. And the very first image we did afterwards is that one. And when we saw that image, no, don't laugh, it was awful. It was just a few quarter of an hours after we landed. At 7:03 we drank champagne, and then we immediately went to the room to take the images, and that's what we call. And it was obvious that together with the other instrument we were moving. And again, that it was really dramatic. And so that was Osiris provided afterwards, splendid images. Really, Osiris did a superb job, and is still doing that. That's the place where we landed before, and this is after, when you see the 3 small places, amazingly. So that's an enlargement here, and that's what we did, and of course we left afterwards. So all this is really brilliant. So after 2 hours, it was almost evident that after some space journey, 2 hours in space, it's not trivial, right? We finally stabilized. We didn't know where and how, but we stabilized because all the record we had demonstrated that we were not moving anymore. So we commented a new set of observation, including a new panorama. And it spent the entire night to wait until the next morning, 4 in the morning, when the next visibility was there. We went there, and it was... and finally we got this image, and really we all around just cried because it was obviously that we were where we wanted to, where we have dreamt to be. And that was the very first image that we showed. And we have landed. Everything seemed to have worked. We didn't know what was broken, but obviously at least that part of the system did work. And that was this camera there. Then we make the next one just close to, and we have the sunlit places here. And this is what finally built this image that we delivered immediately at high resolution, actually, on the website. If you want to take it and work with that, it's in there. There you have all the information there. That's fantastic, because really we had that dream. We decided that really we were there. And so in a couple of weeks we did that. And for the first time we put one of the newest possible system close to the oldest one. There is no, I think, ever landed any system in such an old place. And so we are ready to do what we wanted to, is really to analyze the material out of which we are all here. So that's what we get. But of course there was the entire panorama, so we saw the other images, and one of the images showed that one, and it was like a foot in the air, or in space actually, and we didn't know what was behind. So when we stress a little bit, we have that image which I like, which show that very close by there is this what we call the cliff now, and the bright spot there is no, yes there is, the bright spot, where is it? Yeah, these are just a reflection of the foot here on that, so it gives you an idea of where we are. It's typically a meter away, no more than that. And another one is that, and so for the first time we saw that one of the, we are facing the open sky, and the sun is not very far away because you have glares here, and this is the reflection of the sun on the window here. So this showed that we were a little strangely located. That's one of the two CONSERT antennas, and actually the second was in right here. So we could vision that. And we have a foot over there, so we have a way to localize ourselves. And these are the other images that we got immediately. It's a really stretched image because you have only 2 or 3 dN there, but the noise is less than 1 dN, so you can stretch that. But essentially, it's a black image. Everything is in the shadow. So you have sunlit places, and all the rest essentially is in the shadow. And this is probably the third foot here. So we landed, but probably in a very strange position. And that happened like an hour afterwards. Realized that we were probably something like that. So that's what we immediately showed. Of course, it's misleading because the sun is not really illuminated that here. It's just to show that, okay, we are not horizontally landed as we might have hoped, and it's something like that. So that occurred a few moments after we understood that. And this is a 3D artist view made by the Flight Dynamics at CNES. You don't need to take an image because it's already on the website in this morning, because I gave that morning. So that's probably not true, but I give you an idea of what it is. And actually this is the clip that I showed before. So essentially this artist view is made out of our images here. Not to say that, of course, the background is true. We need to have the DTM from Osiris. That possibly will be done tonight if they finally got the location in the coming moments. And just for you to realize the problems we have is that because of this, the sun essentially goes here, and these are the 4 hours, 33 minutes that are illuminated instead of the 6 hours that half the 12 hours would be. So we have a little limited in the overall time of illumination. So what is the science we did during all the descent until what we call the first science sequence, the FSS? During the descent, we had everything went smoothly and nominally. ROMAP in particular, we have a splendid talk after the break. They make the magnetic sounding from the orbiter to the in-situ science, and of course, thanks to that, they have an idea of what the magnetization of the body is, and you will see the results in a few moments now. it's really great because that gives you a direct outcome in terms of the magnetization of the protosolar nebula as we see it in that material. And then we have also the ROLIS descent imaging that I provided images from 3 kilometers at the beginning, sorry, and then we have the 7 images down to a few meters away, and if Stefano is there, and I hope he is here, that will be presented also after the break. And so I don't need to make more than that. As Jens said, the fact that finally we have a hopper instead of a lander makes a lot of good science waves. ROMAP and MUPUS demonstrated that we were hoping, solar panels and CIVA, I told you, but the ribbons also give us a lot of physics inside, essentially because the question is whether dumping is made essentially by our system or by the soil itself. It's not, the debate is still there. We don't know exactly what the fraction of the dumping in our system. We had 3 systems on board, and the final dumping in our system is what we call the landing gear, and there is an evaluation of what fraction of the energy was dumped by the gear itself, and the rest, the remaining, by the soil. And when you put all that together, you have an idea of what the material looks like at the and we have essentially all the parameters available now, because OSIRIS has given us a lot of information after the rebound, so we know essentially what the altitude. ROMAP gives us the rotation rate, because we see really the rotation rather rapid, actually. I think Uli will go to that afterwards. So we know what the dynamics is, and thanks to that we can reconstruct really the sort of material we have. The idea that, and that comes with many other measurements that have been done, that the top layers, at least, of this material is very tough, very hard, and that we consider that probably the ice at the very top is, just by the thermal cycling, is in a very specific phase, and in the sintering then make the system solid enough to react to us, to enable the rebouncing. And the question, of course, is still there whether it avoided, it amplified by the trampoline-like effect, the rebouncing, or whether it dumped it. We are still there, and that will be, again, soon translated into a paper, I hope. Then we had on the ground what we wanted to. CONSERT, and that will be presented also afterwards, gave the first tomography, a complete tomography in one plane. The ROMAP sounding, ROLIS characterization give us good information on the internal and surface structure. So to go very rapidly, because Matt is already standing here, COSAC PTOLEMY, I won't say about that. They have a lot of things to say about the organics. That will be for the next conference, because of Matt, of course. And okay, what is around? What I said is that this is the cliff behind. When you increase the dynamics, not the dynamic, but the stretching, again, you have 8 dN, including the reflection. So it's very, very interesting, because that tells you, first of all, why we are in a shadow. But what the soft material we have here. As you can see here, this cliff is essentially structured by fractures, which are essentially linear structures here. The same kind of structure that ROLIS probably will show you below the lander. We have the same sort of things. And OSIRIS has shown, and that was shown this morning, same thing at much larger scale. So really these demonstrate the sort of behavior of the ice under that sort of trends. And this is important because you see the same thing here on the right side here, while here on the left side we have a different pattern, a totally different sort of material here, which is essentially the soil rich in carbon grains, the famous carbon-rich grains, which are here. And this is very similar to what we have below the lander on that chart here. So essentially, when you see that again, and I will go rather fast, you see a variety of structures in a very, very close vicinity. And the reason why we like that is not only because we have a lot of diverse material ahead of us, and so at hand, essentially, within distance which are fraction of a meter from the lander, and so directly reachable by our means. But very likely, they are more interesting than the places in which we first touch down. That's one thing. And second, and this is probably what we want to, That diversity reflects essentially the sort of material that we were eager to find when we wanted to be on this comet, because these big body of ices, which are very dark actually, we don't have a clear value yet, definite value of the albedo, but it's no more than 10 or 12% in albedo, although it's ice. So that's really the ice loaded with the organic molecule that we are desperately looking for when we wanted to be there. So essentially, that's what we are ready to operate and analyze when we will be there. So the question, of course, is, shall we be able to do so? Jens already tell you a few fraction of the answer, which I will just complement here. We have a large diversity of materials at hand now for the first time, including possibly the really pristine building blocks of this ice loaded with organics without any processing there. So really, these are the material that you are eager to analyze. Probably by what we did, SD2, the drilling system, is already in a better position to access the soil, because after the rotation we are probably closer. We have also the possibility to lift down the system by 15 centimeters. So probably, even if the first measurement showed that probably the drill did not get a sample back to the ovens, that should be possible now. And the last point is that because of this, this cliff here, we are shadowed enough against the sun that what was previously thought that after March we would be too hot actually to survive, that will be the opposite. So we're in a good shape to really restart the operation as early as possible. The starting point will really depend where we are. If the cliffs are not too high, for the moment the sun elevation is low, it's below the cliffs. As soon as we're on the 1,000 latitude, and that seems to be the case, then rapidly the sun should go over the cliffs, and so rapidly, we'll see what rapidly means, we should be in a position to get much more energy even if nothing else changes. So essentially, we will process all that together just to tell you that what we have not achieved will be achieved at that time. And just to finish with, because Matt is really more than eager for me to finish, it was sort of acrobatic, but we are where we wanted to. It's really a pioneering places where we are now to analyze something which probably will tell us a lot of things complementary to what you have already seen in the, with the orbiter, whether or not these comets took a big role in the emergence of life in particular. Thank you.
Any questions, please? Yes.
I have one question. My most important question I had coming here was, when I look at your lander images of the surface, which are fantastic, in no place do I see what looks to be like icy dust bunny. Very loose, porous, fluffy, weak material. I understand that, so that's arguing that maybe all the things that we're looking at have been resintered, or maybe what Olivier Grossoma is arguing is that maybe the comet is more solid in local areas or in small scales, and there are big voids inside. Would you like to comment on that?
Well, I'm not sure I'm the best to comment on that. As you saw in the images, which is still on the left here, we are you have the entire variety of material, from the block of ice loaded with organics again, up to the fine grain, which is essentially organics, because that's the very dark material that we see essentially everywhere else, if you take the Osiris images or even our images elsewhere. So we have the variety of material out there. Do they come by outgassing from a single sort of material? I would guess so, that we got to demonstrate that. So it might be that when you take this block of ices and you start to sublimate that, the end out product will be this very fluffy molecule, fluffy particle that you get, and which are deposited elsewhere on the surface. That would be my suggestion.
Okay. Thank you.
Thank you.
Just a quick one. Can you bring your glasses, well, those glasses down to the front? Please don't walk away with them.
And
Claudia will come and get you. Or on the back, yeah. The back.
so, folks, you heard about the surface today. You heard about the gas. You heard about the dust. You heard about plasma. So, to make your experience complete, I would like to solve the last controversy of the comet.
Churyumov-Gerasimenko.